Right, it's 2 o'clock, everybody. I hope you can hear me. Um, you might see my name in the list, John B. That's only because I've got a second computer running just to make sure that my voice is getting out there, but it appears that it is. So, welcome to the wholesale webinar. You have to unmute the sound. Obviously, if you can't hear me, you need to unmute the sound button, but I'm sure you know that now. And when we get to any questions and answers, you can see that you can type your name down in the bottom, or at least type your message in the bottom, and hopefully we can answer the questions that you put forward, should there be any. Okay, so straight on to the presentation. And the presentation today is all about the wholesale. It's a tool that's used in electroplating, has been for many years. So I'd like to start, first of all, with a little bit of background as to how the wholesale came about. So the history of the wholesale. Who was R.O. Hull, the man who actually invented it? And why did he invent the wholesale in the first place? What was the purpose of it? And what do we get out of the wholesale? Okay, so we're going out of a blue screen onto a normal presentation screen. And Mr. Hull was born in the USA, a good old American. And he took up a position in his family chemical company. He was born into a chemical company. I say he took up the position, and he was actually quite a clever person. The company was based in Hawaii, and it manufactured specialty chemicals and what we know now as surface technology. He was a very clever man, actually. He was into sort of a lot of modern day, well, what is now modern day chemistry, but obviously it was in its early years then, and we've learned a lot more since. But he was, if you like, a bit of the father of chemicals and cleaners and things like that. And by 1935, the company was supplying additives to the surface engineering industry under the name of R.O. Hull, which became later known as a company called Roco. Now, I don't think Roco exists anymore. I think they were bought out by M&T, which is now Atotech. But nevertheless, they were a very good company and supplied some extremely good chemicals. He worked for the company supplying corrosion inhibitors, and he found that these chemicals had a lot of surface active characteristics. And he realized that these additives could be used for electrochemical processes in the electroplating industry. And this was later the driving force for most of his activities. He also realized that some of these additives that they were using, when they were used in electroplating chemistry and the current was supplied in the electroplating, that you get different finishes. And this was sort of the birth and the early days of brighteners and levelers and additives that went into electrochemistry. And obviously, to learn about what these additives were doing and how could you understand them better, this is where he came to the idea of building a plating cell to see if he could understand how at different current densities the additive was having the effect on the surface finish. And this was his design. I'm sure we have all seen a wholesale. It's very simple, not a complicated thing. Longer on one side, shorter on the other, anode, cathode. And these were the dimensions of that he used in obviously good old imperial inches, which the Americans use. And he used a 267 mil solution level. Why 267 mils? So this depth of 2.5 inches gave him the volume of 267 mils. And if you add 1 gram of the additive, that's equal to 1 ounce in a US gallon. And obviously that's what he worked in. In the UK, they reinvented it to be 320 mils. So 1 gram of additive was 1 ounce per imperial gallon. And I must admit, when I first started in the electroplating industry back many, many years ago, everything was in imperial gallons, ounces and pounds. Grams and litres hadn't come into being then. And I must admit, it was a much more complicated system than it is now. So what does it claim? It claims to optimize the current density range. So you can actually work out the best current density range that the additive is having. It optimized the additive concentrations. You could tell from the results that you got on the cathode, the additive concentrations, whether there's too much, too little, whether it was having an adverse effect. It also was very good at producing impurity effects. If there was any impurities in some of the deposits, you could actually see that, such as, for example, if you get too much copper in an electrolytic nickel, in the low current density, it will be black. And the same goes for zinc as well. So you could identify these and learn how to get rid of the impurity to get it back to a good new solution. So looking at the manufacture of a whole cell, it can be made of any sort of plastic, but normally they're perspex or polypropylene. The perspex ones are very good because you can absolutely see through it. Polypro is more opaque, but perspex is very good. It can be just a single cell, just a simple cell, nothing in it, just the shape that you see and the anode and the cathode. It can be fitted with an agitation pipe, such as an air sparger pipe. And it can have, and expensive models often have their own heating facilities. So we'll just look at a quick schematic of what the whole cell is. As you can see, you've got here a longer side and a shorter side. This side is the anode. This is where the anode is. You should, when you have an anode, obviously it will wear down, but you look to try and accommodate most of the shape of the back end of the whole cell. We then have a cathode, which you can see is at an oblique angle to the anode. And this is what is very good with regards to the whole cell, because obviously this is a shorter distance for the ions to travel from A to B and a longer distance from there to there. So obviously this becomes a high current density effect, and this becomes a lower current density, with obviously all the other varying current densities in the middle. There are some whole cells out there that are the reverse of these, but the same principle applies. It's still the short distance, as long as you remember to read them the correct way around. And most whole cells are left-hand side of the panel is the high current density end, the right-hand panel is the low current density end. Here I've done a schematic of an air agitation pipe, which would just be behind, which would be, beg your pardon, in front of the brass panel or the plated panel, with air flowing over the surface. This one is showing a stirrer, which would, if it is, say, in an inductor system and the cathode doesn't move and you have no air, this will spin round and supply a degree of agitation across this face here. And obviously a rectifier, not the best looking rectifier in the world, but you get the idea. Obviously the anode and the cathode, and some sort of method here to vary the current that you're putting on the solution. And by kind courtesy of the old Canning handbook, there is a perspex whole cell. It's not the best import of a picture, but you can see basically what it is. This is an air agitation, a downward sparge pipe there with small holes across the surface, the cathode there and the connections, and obviously the anode there. So let's just have a look at each individual component. The anode. Usually the anode is made of the same material as the metal being deposited, as in the plating solution. So copper for copper plating, nickel for nickel, zinc for zinc. If you had cadmium, if you could do cadmium, you do that. Silver plating. Or you can have, and it's thinking about it, an inert anode, such as platinized titanium for gold solutions, or antimonial lead for hexavalent chrome solutions. But the anode must mimic what you are using when you want to conduct the test. The cathode. This is made from either polished brass sheet, and they are used basically on things like nickel, copper, gold, silver plating solutions. They also used on chromium plating as well, but then you would prepare the nickel onto the brass sheet. So the brass sheet would be plated with nickel prior to plating with chromium, as it would in practice. Or you can have a polished steel sheet, which is used for zinc, cadmium plating solutions, those type of solutions, as these type of solutions very, very, very rarely plate non-ferrous metals. They're nearly always plating seals. Right, the next thing we'll have a look at is agitation. The agitation used in the whole cell should always replicate the type of agitation that you're using in the process. Air agitation first. There are still many, many plating baths out there that use air agitation, even though obviously people would prefer now not to use them because of airborne spray and things like that. But yes, air agitation is still used. So some method of low pressure pump, which usually a simple thing like a fish tank bubbler will do, and that's as long as it will blow a uniform surface of bubbles over the cathode, that is fine. It doesn't have to blow the solution out of the whole cell itself. Or you can have obviously mechanical agitation. Obviously, you can't move the cathode. The cathode is fixed, otherwise you'd have varying current densities over it. So you keep that fixed, and you need to move some method of employment of moving the liquid. So a mechanical stirrer that will stir the solution round, which would be equivalent to eductors. In a lot of Europe, they actually use mechanical agitation, where the cathode bar on the electroplating tank is moving side to side. And some people have devised methods of putting a small paddle in front of the cathode and sliding that across the surface. But as long as you're moving the solution and getting some representative of what's going on in the main tank, it usually suffices. So now we've got the cathode, we've now got the anode, we've now got the agitation. We now need to prepare the cathode ready for plating. And this is one of the most important steps. If you get this wrong, if you try and interpret the solution results, they will be incorrect. I've seen many times people trying to just pull off the plastic sheet, put it into the tank and get some dreadful results and wonder why it doesn't represent what's coming out of the plating tank. So this part is really, really important. And I can't stress enough that if you can set up a nice little cleaning system for it, then it will be the best way. As I say, brass whole cells usually come with a protective film, and the film is there just to protect that polished surface and prevent any further scratches on it. Steel whole cell panels sometimes have a very light oil film. Again, they've been polished, not to a massive degree, but they have been polished, and it's just to protect them from going rusty. Sometimes they have a protective film, but it's very commonplace just to have a very light oil film on the surface. So, preparation of the cathode, how do we go about it? What is the best way of doing it? So, as I said before, if you just remove the film and use that surface to plate on, it will give you incorrect results, as the metal being deplated will be depositing on anything that's left behind that sticky surface. So you need to make sure that it is good. Cleaning the cathode should be the same as if you're cleaning a part ready to plate. It's no, why should it be any different? That's what you want. The results you want to see, want to typify what the plating bath is. And it's very important to make sure that you're doing it in a similar fashion. So the first part is you degrease the cathode. You then rinse the cathode. Acid dip the cathode. Rinse that off and then test it in the electroplating bath. So degrease the cathode, rinse the cathode, acid dip, rinse and electroplate, just as it would be in a plating line. So a small scale setup is obviously the ideal way. Not everybody does this, but if you can set up a small little scale method, it makes life very, very much easier. So if you can get hold of a 5-litre stainless steel beaker, which you can heat, a running water rinse, that can be just literally under the tap, a small beaker of sulfuric acid for brass wholesales, 10%, or I've always used 25% hydrochloric for steel panels, just to neutralize the cleaner and provide a small amount of acid surface. And then again, a running water rinse. And obviously a rectifier for carrying out the tests required. 0 to 10 amp DC is usually more than enough for what you want. You can get away with, say, 0 to 5 amps, but if you're not doing chromium, if you're doing chromium, you do need a 10 amp rectifier, and probably around about an 8 to 12 volt rectifier as well. So just going the degreased method, using a metal container, you add your non-ferrous metal cleaner, exactly the same as you probably use in the plating shop, made up around about 50 grams per litre. You make the container the anode and the brass steel panel as the cathode. You apply a current of around 5 amps to the panel, and obviously the panel will gas. You make sure that it doesn't touch the sides of the beaker, otherwise it will short out. But the resultant gassing that comes off the surface, and the fact that the cleaner, which I must admit I didn't write down, would probably be around about 50 or 60 degrees centigrade, that will remove any oils off the surface, whether it be steel, the oil off the steel panel, or any finger marks, or the resultant plastic that was on the surface, any sort of adhesives that are used on the surface, it will get rid of those. And then obviously you clean for about 2 to 3 minutes. 2 to 3 minutes on most wholesale panels will see it absolutely fine. So after degreasing, you transfer the cathode to a running rinse to ensure that all the cleaner has been removed. And if the panel has been cleaned correctly, there should be no evidence of water breaks on the surface. And that part is very important. If there are water breaks, then there is something left on the surface which can interfere with the results that you're getting on your test. Remember that a lot of these tests are carried out on bright solutions, and if there's anything underneath, it'll just be magnified through the bright solution. And what you won't know is it a fault in the cleaning operation, or is it a fault in the solution? So always look out. If there are water breaks, then go back and re-clean it again. So again, after dip the panel in either 10% sulfuric or 25% hydrochloric acid. For brass, 1 to 2 minutes just to neutralize the cleaner. For steels, I always immerse them about 3 minutes, just basically to get a very light etch on the steel. That's the sort of thing you would be doing in the line itself. It neutralizes the cleaner as well, but yes, it provides a light etch to the surface. And after acid dipping, transfer the cathode to running water. And again, make sure that there are no water breaks on the surface. After acid dipping, well, if you've got to the stage of acid dipping, there shouldn't be any water breaks there anyhow. And definitely after rinsing, there shouldn't be any water breaks. But if sometimes the acid is old, it's been in the tank a long time, because bear in mind these solutions are used not perhaps every day of the week, then if there's any contamination got in, it could lead to a little bit of water break on the surface. So always look to make sure that it's water break free. It's then transferred to the whole cell, and which has the electrolyte in that you're testing. So it could be copper, it could be nickel, whatever it is. The volume of solution in the whole cell is important. In the States, as I mentioned before, it was 267 mils. And the reason was 1 gram of additive was equivalent to 1 ounce per US gallon. Or I think, if my maths is right, about 1.2 grams per imperial gallon. Obviously, nowadays we're all metric, so you can come down in volume to 250 mils. And so 0.25 grams or mils of additive is approximately 1 gram or 1 mil per litre addition. So we look at the electrolyte itself. So after determining the volume, you need to warm it up. For example, if it's a nickel, make sure it is done at the correct temperature. If it says room temperature, it doesn't mean room temperature on the 31st of December or the 1st of January when it's only 4 degrees. You must make sure that you're running the test at the same time, at the same temperature as the bath is running. The correct agitation should be used, again, as I mentioned before. If you have air agitation, use an air agitated whole cell. Acid zincs will use air agitated whole cells. Mechanical agitation, or no agitation at all. Sometimes you have what's called a still bath, and then you have no agitation. So the amount of current and the duration of the test. So for nickel, copper, zinc and cad, it's usually somewhere, and most bright plating solutions, you have 2 amps for 10 minutes. If you want to emphasize the effect of an impurity, you can go down to 1 amp for 15 or 20 minutes. That will give you, as you can see there, 2 amps for 10 minutes is 20 amp minutes. So it's normal to have 1 amp for 20 minutes to give you the same sort of thickness. But because it's a lower current density, a lower current, it will become a lower current density over the panel itself. If you're looking at the bath is burning for whatever reason, then somewhere, and your normal current density is around about 3 amps per square foot, or 30 amps per square foot, sorry, or 3 amps per square decimeter, 40 amps per square foot, 4 amps per square decimeter. Then if you apply 3 amps for about 5 minutes, that should be able to determine whether it is burning and it is a current density effect. If you're looking at hexavalent chrome or even trivalent chromes nowadays, 5 amps for 3 minutes for the decorative type. And if you're looking at hard chrome, that is where you need the 10 amps for 1.5 minutes, obviously because the current put onto hard chromes is very much greater than it is for ordinary decorative measures. Right. This is a current density chart, and I have got this from the back of the good old canning handbook, which is the Platers Bible. But basically what we're looking at here is, this is the whole cell panel. Okay, this is the high current density end, This is the low current density end, and obviously these are the current densities across the surface. Now, if we look in good old-fashioned money of amps per square foot, you can see that at point A, if we had 1 amp applied in the whole cell, that would be equivalent to 40 amps a square foot. Likewise, 2 amps would be 80, because obviously just multiples, 120. And as you can see, as you go across, so when we're down this end at N, if we have a 2 amp whole cell, for example, a 2 amp whole cell, yeah, then that's going to be around about 1 amp per square foot. And at those sort of points, if it was a bright nickel, if you were contaminated heavily with zinc or copper, that would be showing up as a black area. Likewise, if you look down this end, this is in amps per square decimeter, which is the more modern way, and the lowercase shows exactly the same thing. So this one, A here, is equivalent to 5 ASD, 10 ASD for 2 amps, 15. And you can put the chart there and measure where it is against things. So we'll go on to show you how to do that. Now, it's very difficult to photograph whole cells, but I've tried the best I can. But I'm using here chromium on bright nickel, basically because it does show it up very easily as to see what happens, just to explain how to use the chart. So this is a nickel plated whole cell. And obviously here you can see the blue chromium, which stops plating here. But what is this current density? Now, this is a whole cell that would be plated for 5 amps for 3 minutes because it's decorative. So if we place, as I said before, the whole cell against the chart, you can see where the current density is, or which letter it comes up against. So in amps per square foot, it's nearly at D, but not quite. In amps per square decimeter, yeah, it's just a little bit further away from D. It's only because of the spread. But you can see it's not down here and it's not up there. Okay, so if you now look at amps per square foot, as we said, there's the D. We're nearly at D. We applied 5 amps for 3 minutes. The 3 minutes is just a standard time of plating. So you can see here that we are just above 100 amps in a square foot. The C would be 125. This would be about 100. So let's just say, for argument's sake, it's around about 105 amps per square foot. So if you were applying, just for the sake of argument, to a plating bath of chrome 100 amps per square foot, and you suddenly realized you weren't plating in much lower current densities, you can see from the test that that has proved that that bath is not in good condition, because theoretically it should be down here somewhere. I've done the same thing again when it appears. Here we go, in amps per square decimeter. And again, oops, I've got amps per square foot. I apologize. What's that one? My mistake. If this, let's try this. There we go, amps per square decimeter. So again, as I said before, there's C, there's D. Look at 5 amps applied. So it's somewhere between 15 and 10 amps per square decimeter. And again, if we scale it across, we're looking somewhere about 11 amps per square decimeter. So whichever scale you work in, whichever method you work in your particular industry, whether it's amps per square foot or amps per square decimeter, then obviously you can ascertain what the current density is that the cutoff point for chromium is on this particular instance. Right, so I've highlighted here, obviously highlighted the area that we're looking at. Obviously, if you'd have plated at 3 amps a square decimeter, you'd be on this scale. But what you've got to see is that, for example, you can see here that this is round about 11 amps a square decimeter. If I'd applied only 3 amps to the whole cell, I would be somewhere between B and C, because then I would be on this scale. So it would have only covered about this far. So it's very important to know what the current is that you're applying so you get the correct results. There is a formulation in the Canning Handbook. I haven't put it on here, but there is a formulation to work out how these current densities are actually obtained from the distance. But in real terms, just use the chart. It's the simplest way. So that's more or less what a correct chrome should look like. You can see by what they've done to the chrome and cured it, it is now moving down here, which is giving you something like the correct result. So here we're just looking at a few examples of whole cells. As I say, they're not easy to photograph. I did struggle a bit trying to get these. But this is an acid zinc. It's very difficult to see, and these panels have been around, but there is some low current density faults down here. Again, I apologize that you can't necessarily see them. You'll just have to take my word, but there is some faults down on this particular part. Another good test that you can use for the whole cell is by plating a part that you say is knowing good. You can get some idea of what the distribution is, or the throwing power of the electrolyte. So this is the high current density area, this is the low current density area. If you pick 2 points from the chart, say, I don't know, 40 amps a square foot and 10 amps a square foot, and you plate it for a period of time. Now, in this case, this would probably be plated for 20 minutes to get a reasonable amount of thickness on. You can see how much zinc you'll be putting down at that particular point and how much you'll be pushing at that point. And if you know the characteristics of the zinc, you can tell whether it's still plating well and the additives are right. Normally, if the additives start getting too high, you will start to lose thickness here and gain thickness there. If it's too low, you get other problems like burning at the edges here and poor distribution. But this is a good simple way of measuring a distribution tech. You just literally put 2 points, plate it for about 10-20 minutes, and then measure the thickness at the 2 points, and you can get an idea of how well a solution is doing. If you look at this one, this is an acid zinc, and you can see it here. You can see here these little, they're often called Prince of Wales feathers, these stripes here. That's indicative of too much brightener. This was an air agitated bath. Most acid zincs are air agitated, and when the bubbles come up and the brightness is carried up with the air agitation, it gets co-plated out. And if there's too much brightener, you get this ridge. If you looked at this edge on, it will have a surface effect that looks like that. And you can see there and there and there. They were often known years and years ago as Prince of Wales feathers, especially in bright nickels. They do splay out a little bit like a Prince of Wales feathers, but you can see the ridges in there. The other thing you can see on this one as well, you can see where the edge of the build-up of zinc on the edge. You can see the thickness of it, and also the fact that it's burnt as well, which is probably indicative of too low a metal content in the zinc, which makes it burnt. As could be the case, you have too low a metal, you may have the correct amount of brightener, but it will still be the incorrect amount for the solution, and this can give you that effect. Right, so this one is chrome over bright nickel. This is, again, 5 amps, 3 minutes, and it's a thing called whitewash. I know probably a lot of you may not have seen chrome plating, or you've seen chrome plating, but you don't experience it yourself. But hexavalent chromes are quite simple chromes. They are just literally sulfuric acid and chromic acid. But if you get it wrong, in this area here in the heart, you get these white splashes. This is nice shiny chrome. The nickel is being reflected through the chrome and it's nice and bright. This is just white. and whitewash is usually an imbalance between the ratio of the chrome and the sulfuric acid. That's a good chrome. That's what you would expect for a chromium plating solution on a good nickel base. It's very rare you ever chrome straight on brass. It doesn't tell you anything. Nearly all chromium is plated on top of bright nickel, and I'm talking decorative here, not hard chrome. And it does give you an example. It does show you how the chrome is plating, and in this case this is a typically good chromium plating bath. If you're using hard chrome, you can use a steel wholesale panel for that, because most hard chrome goes onto steels, and you would plate directly on and you would see the results of that. This is an acid zinc. They tell me this is a good acid zinc. You have to believe me. Yeah. As I say, these panels have been around a long time, but it is nice and clean from high CD to low CD, although it doesn't look it, obviously. There's no evidence of burning here down this edge. There is no evidence at all of striations of too much brightener. The other thing I will just mention is when you dry these panels, when you finally rinse them and got them out, light tissue is good, hairdryer is very good. Some metals like zinc, which is much softer than say nickel and chromium, sometimes rubbing them with a towel or with the tissue can scratch them. So the hairdryer is quite good. And there you must make sure that this could be just drying stains, probably nothing indicative of the bath itself. And the final one is a bright nickel, which there isn't much to see. It's just a nice bright nickel over a brass wholesale. It's got no, as you can see there, it has no cleaner faults whatsoever. There's no marks on it. There's no burning in the high current density area. It plates all the way down, and it's nice and bright all the way down. I haven't gone into all the different types of results that you can interpret. And again, I will refer you, because most people have a canning handbook, and therefore if you look in the back of there, it gives you some idea of what's happening. But if you do ever have the time and you really want to understand, say, your particular plating solution, let's say a bright nickel, you can always make a bath up and very small amount of no brightener at all, add brightener, keep adding brightener, and just get yourself a series of wholesales and mark on the back what you're getting. This is a result, a dull, no brightener at all, adding brightener, you get the results. Often people keep these, they lacquer them, or they put shrink wrap around them to protect them and use them as references. Okay, so that's an outline about the wholesale. I have here a little video of the wholesale. Now, if you go to the bottom of your image here where my pointer is, you should have come up, or just outside it, you should have come up a little speaker which is on. Now there is some music on this. This is one that I filmed myself, but I think it might be an idea just to switch the music off. It's quite heavy towards the end actually, but and then we'll talk it through to show you the actual cleaning methods of the wholesale. As you can see from the front picture, this is a Perspex wholesale. It was a good old Lee Rennell. That was the name from the past. You can see the 250mm mark, the 267 if you're using it for in America. And the anode, well, you can see where the anode is actually being used and worn down. Here's the air pipe, and it runs across the bottom. So if we start the video off, hopefully it'll all work. He says. Right, so I've, as I say, I've put it with graphics on there. So it's a simple and rapid method of testing over a wide current range, density range, and purification, etc. So this will show you how to carry out an air agitated whole cell test on an acid copper plating solution. So again, we'll go through the equipment that is required. So there's your whole cell, air agitated whole cell. You can see the bar at the bottom. There's the anode, and obviously the clamping the anode to it. There is the brass whole cell, and there is the protective coating on the whole cell to remove. And again, I stress the cleaning of the whole cell to make sure you don't just peel back that protective coating. And we'll show you how the clean brass whole cell panel. So you can see here, 5 litre beaker. This is the cleaner. There's a current on there which is about 5 amps for 2 to 3 minutes. This is a lovely picture of my hand and glove, but you can see that it's fizzing slowly. So after cleaning, you immerse it in water. Now I did say rinse under running water, but this is just to be shown for the video to show you, to explain it a little better. And it saved me moving the video camera, keep moving the video camera over to the tap. But we're swilling it off with the ionised water here. That isn't mandatory. You can rinse it in tap water, that's fine. It's really just to make sure it's nice and clean for this. And what you should see is no water breaks. And as you can see there, the water is clinging onto the surface. And then the whole cell is immersed in 5 to 10% sulfuric acid, just to neutralise the alkalinity of the cleaner. Now you can use that as a holding area. You can leave the panel in there while you go and fill the tank up, your whole cell up. It will do no harm. But there I've just shown it being used and rinsed again to make sure again there's no water breaks, and there shouldn't be. If you're going to hold the panel anywhere, don't hold it in the water, hold it in the acid tank, because obviously you will oxidise the brass back up again. Or in the case of steel, you could actually, if it's a good bit of quality steel, you could put a light rust film on the surface. Again, no water breaks. So here we have our 250 mils, and again I've just outlined why it was 267. 2 gram additive, 1 ounce per US gallon, so 250 mils makes life a lot easier. So we've measured out 250 mils acid copper solution. This is an acid copper from a printed circuit board bar. And you can see just a shadow whether there's 250 there. There's the whole cell, and now we're putting in the chemistry into it. The air sparge pipe is already connected, so you can see the bubbles there being produced across the surface of the whole cell itself. Now it's very important when you put the brass whole cell in, timer set for 10 minutes because we're doing a 2 amp for 10 minutes, is when you put the brass panel in, you must make sure that it does go behind the bubbles. I have seen many times people, some whole cells can be a bit tricky, but yes, make sure it's behind, and obviously you can see there it's set for 2 amps, and we started the timer for 10 minutes. Now obviously we're not going to wait 10 minutes for this to happen. As in any good video production, we can accelerate time, but there you see actually the bubbles and the whole thing plating. You can see the copper forming on the surface there. So after the 10 minutes, you disconnect it, take the cathode off, and you've got your whole cell. Now this whole cell doesn't look particularly good. In fact, it looks dreadful, but there is a reason for that, which I will explain when it's finally finished and drying. So after water rinsing, it's swirled down again with, I've used DI water, and then I've dried it with a small amount of tissue. And again, if you can use gloves on rather than use your fingers, you get a nice clean finish. And then a small hairdryer, down to boots, go and get yourself a nice little hairdryer, just to dry off the surface of the water. You can see it coming quite nicely off this copper here. And that's the back of it as well, so it's plated all around the back. Okay, so what I think actually it's moved on. I don't want more videos, thank you. Hopefully it's working. Yes, the finished panel. What you can see there is a heavy burn, and what that is actually showing is the amount of brightener that's in the actual bath. So I'll talk about that when this video is finished, but in some instances you can't use air agitation such as cyanide silvers or alkali zincs. So this is just a little setup here you will see with an agitator and a magnetic stirrer. Again, we do have heating down there, but obviously the heating isn't on. If it is heated, then you can get yourselves a water bath, and you raise the temperature of that to get the temperature within the whole cell to the right temperature. So you've got a setup like this, water bath on a heater, and this one's using a magnetic stirrer. So if you want 60 degrees in your tank, then you need something like 90 degrees in the bath just to keep the heating, and that's showing it with air agitation. Okay, little promotion there. So now we've finished, I'll just say thank you for listening, and I will throw it open for any questions that you might have. If there's anybody got any questions for me, please type in the bottom, as I said, down at the bottom corner, which is down here, and I will endeavour to answer it for you. There is somebody typing. Canning Handbook is out of print as one there and has been for decades, although there is a reprint under a different name on Google Books as an ebook. Any idea what it's called? No, I don't have an idea, but I understand that the Indian corporation, one of the companies in India, has actually reprinted the Canning Handbook. And I think if you get in touch with the IMF, there is a gentleman called John Torr who's in the IMF, and he may be able to point you in the right direction. If you want to contact head office, then you can actually possibly get you a copy of it. It's not a cheap book at the end of the day, but it is God's gift to the Platers Bible, really. I've also been asked a question, will the presentation be available later? Yes, is the answer. It is being recorded, and I will I'm in the process of producing an IMF YouTube channel. I'm hoping to get the link on very soon for everybody. I will issue the link out to everybody who's been here. And then you can have a look at the presentation again. There is also on the YouTube channel, we had a presentation, a seminar last week, all about aluminium and aluminium plating, and I'm in the process of uploading all the presentations for that as well. So what I'm trying to do is to get the IMF on YouTube so you can look at these things and actually physically see them, and hopefully they will be of interest to you. I've got a question, says John, please explain the issue with the copper panel plated in the video. Yes, I didn't highlight it. It's difficult for me to stop that, but what you saw was a very, very large burn on the left hand side and then bright on the right hand side. This particular acid copper is the way of determining the amount of additive in the solution is by the degree of burn from the high current density. So once you get your panel out, you use a ruler and measure in millimeters from the high current density to where the burn goes into a bright area. Can't remember the numbers, but for example, if it was supposed to be 20 millimeters was perfect and it was 40 millimeters, that would show you that you require something in the order of a little bit of additive to bring it back. If it was completely bright all over, you actually have too much additive. And because this particular bath is used for printed circuits, that may upset the throwing power of the solution and the deposit that goes down the circuit board hole. Any other questions? I hope you enjoyed it. We are having another webinar in November, which is going to be given by Safilco, all about pumps and filtration. But what I am trying to look at for next year, as I am part of the sort of education and M&M's group, is to bring more presentations which are together with the courses that people take. So I gave a paper on the electroplating of aluminium. I did seriously think I would do that also as a webinar for everybody. So you might find that interesting. The other thing is that I'm looking at also doing a webinar next year on pre-treatment. I did a paper many years ago on pre-treatment, which was published, and it's probably the most important thing in electroplating, in any form of plating, is pre-treatment. So I'm hoping to perhaps get that out as well. I will try and take some video of some pre-treatment plants. I'm not actually going to say whether I'll be able to or not, but a picture tells 1,000 words, so I'm hoping to do so. I hope you've enjoyed it. If there are no more questions, yes, somebody is typing now. I've got 2 or 3 typing now, just when I thought I'd get away. And thank you for the compliments, by the way, that I've had, which is good. If any of you can think of a webinar that you would perhaps like the IMF to put forward, please contact the IMF. You could contact Helen at the IMF and just say, would it be possible for John to put a course on X, Y, and Z? What I can't do is a course of the answers for the examination questions. Not allowed to do that. But yes, if you feel as though there is something that might be of use to you, please, because it's difficult sometimes to think of what else to put on. But I think that it's interesting that these webinars are now getting out to a lot of other people. And it's nice to see that people probably think that they are of a lot of use. So it's not wasted time, so to speak. Okay. Thank you very much. Have a good day at work again, and I will hopefully see you at the next webinar. I'll get out the dates for you. It's sometime in November. As I say, it will be with Safilco and filtration and pumps. Thanks for listening. See you soon.